Hello, AP Physics students. Hope you're ready to power up here with some examples from Chapter 6. Today we are going to be starting in on Chapter 6, problem number 59. And this problem states, if a car generates 18 horsepower when traveling at a steady 88 kilometers per hour, what must be the average force exerted on the car due to friction and air resistance? All right, good problem, right? Fun to talk about horsepower and cars and all that good stuff, right? So figure out how fast you can go in your speedy car, right? All right, let's start with our, as we always do, with a good old free body diagram. So we got our very aerodynamic car here. We got weight going down. We've got our normal force up. The engine is exerting some type of force on the tires, which is making the car go forward, right? So I'm just going to call that force F. And then we have some type of resistive force. I'm going to call it F sub air, right, for air resistance. So the car is experiencing air resistance, friction, those type of forces that are slowing it down, okay? So there we go. There's our free body diagram. What else do we know? We know that the car is traveling at a constant speed, right? And constant speed without changing directions. What does that mean? That means acceleration is zero, right? Which means by Newton's second law that the net force is zero, right? So force of air resistance must equal the force the engine's exerting forward, and the normal force must equal the weight up. Pardon me, weight down, normal force up. Cancel each other out. Those little words, constant speed, right? They mean a lot. Okay, what else do we know? So we know that the speed of the car is 88 kilometers per hour, right? And of course, you're thinking what I'm thinking here. Ooh, kilometers, hours. Ooh, we don't like that. Let's get rid of those. So 1 kilometer is 1,000 meters, showing my dimensional analysis here. And 1 hour is 3,600 seconds, right? 60 squared seconds, right? And kilometers cancels and hours cancels, and I'm left with meters per second, and that turns out to be 24.4 meters per second. Can never go wrong with meters and seconds and kilograms in physics, right? Okay, so we know our speed now, our nice constant speed. What else did they say? They said the power exerted by the engine is 18 horsepower, right? And I know what you're thinking. Watt is power. And I say, no, power is measured in watts. Ah, little joke there. So power is work per unit time, all right? So the unit for power, or work per unit time, would be the unit of power, right? Would be joules per second, right? And a joule per second is also known as a watt, named after James Prescott Watt, or W, all right? Now be careful in these problems that you don't confuse W for watt and W for work, okay? So SI unit of power is the watt, okay? So what's a horsepower then? Well, back in the day, a horsepower was the power exerted by one horse. And now we have a nice little conversion here. You won't have to memorize this, but it's a good number just to have in the back of your head. 1 horsepower is a 746 watt power, right? So if I have a 1 horsepower electric engine, say, it would draw 746 watts out of the outlet it's plugged in, assuming there's no, resistance or that type of thing. So if I multiply this out, the engine is exerting 18 or a power of 18 horsepower, which turns out to be 13,428 watts, right? So every second that goes by, this engine does 13 kilojoules of work, right? 13,428 joules per second, right? Pretty powerful engine, right? Okay, so we know what power is, we know what a horsepower is. Well, let's attack this problem here. Well, first of all, let's just say that the force the engine exerts forward is equal to the air resistance force backward, right? So, and work is force times distance. So the power or the work that the engine does is equal to the power or the work of air resistance. Since these forces have to be equal, now this guy would be doing positive work and the air resistance would be doing negative work, okay? Okay. So let's figure out our power here. So power is work divided by time, but work is force times distance divided by time. And I'm going to write this as force times distance over time. Well, if you're going in a nice straight line at a nice constant speed, right, what is distance over time? That is just your speed, right? Speed, F times V. So this equation breaks down to power is equal to F times V. Or in this case, for this equation, we would arrange this to F equals P divided by V. All right. So the power that this force is exerting, right, is equal to P divided by V. Or if we plugged in our numbers from above here, we do 13,428 divided by 24.4, and we would get 550 newtons. Okay, so the force that the engine exerts forward is a 550 Newton force, and that is also equal to the force of air resistance, right? These forces would be equal in magnitude, opposite in direction, and we know that once again because of the constant speed. All right. Okay, nice work, physics students. As promised here, we'll get you your hilarious cartoon as your... And here's our reward cartoon. Oh, this looks funny. What do we got here? We got the roller coaster, the Death Demon. Now, Paige, at this point, we're essentially nothing but potential energy, which is MGH at the top of the roller coaster. Hey, this is a cartoon about physics. As we go down the hill, this energy is converted into kinetic energy, 1/2 mv squared. So a quick and dirty approximation of our speed at the bottom of the drop, like this, might assume the change in kinetic energy is equal to change in potential energy and give us is equal to V is equal to square root of 2g negative delta H. But, in fact, our cars are constantly losing energy to friction. This is why the first hill has to be the highest. See what I mean? Now, in order for the car not to fall off the track here, Jason, please! This is a roller coaster. It makes me sick enough as it is. Oh, my calculator. Oh, that funny foxtrot. Oh, good stuff. Good stuff. All right. Nice job, AP Physics students.